My name is Trevor, and welcome to Datature Tutorials. Today, we're going to be learning how to annotate and train a 3D medical segmentation model using Datature's Nexus platform. 3D medical segmentation is very similar to 2D segmentation. In 2D segmentation, you attempt to classify individual pixels as being a part of an object or class, whether that be a class you're interested in identifying or a background or empty class. In 3D medical segmentation, there are a couple of changes. Other than the specified domain, we are now handling volumetric inputs rather than the usual 2D image. Subsequently, we are now classifying individual voxels, or a three-dimensional equivalent of a pixel, as being a part of an object or class. Such a use case would be tumor segmentation, spine segmentation, or organ segmentation. However, today, we will be training a model for multi-organ segmentation. Let's get into it. To get started, click Create New Project. A pop-up window will appear and prompt us to enter a project name, which we'll call ours Demo Organ and Bone Segmentation. We will then select a project type of Medical 3D Segmentation, which will automatically set our content type as NIfTY and DICOM, and then we'll also use multi-region project localization and data localization. From there, click Next Step. Once clicked, we'll be brought to the dashboard page of Nexus. Here, there isn't much information, but you can see that we display statistics on your dataset and annotations, as well as neural network trainings. The first thing we want to do is upload data to the project. To do so, you can click Upload within the Tag Distribution region. This will bring you to the Upload Assets tab in the Dataset section. Now we can upload our assets. To do so, you can click on the Upload Assets section and select the files that adhere to the upload limit. Then click Upload. Once we click Next, we're prompted to enter the groups to help organize our data. For now, we'll just have everything default to the main group, so we'll click Upload Files. Now our files are prepared for upload. Once they've uploaded, our assets will need to be processed, which can be done in the background. While assets are processing in the background, you can upload other assets, which will also be prompted to run in the background. After uploading, the status of processing assets and the results of those processed will be available for viewing by clicking the notifications icon in the top right corner. To view our uploaded assets, we can click on the View Assets tab. Here, we can view all of our uploaded assets, which are now stored into your personal cloud on Datature, meaning you can access them across multiple devices. Now, we'll talk about asset annotation. To get started, we'll need to head on over to the annotator. From here, there are two ways that we can access the annotator. We can either click on Annotator underneath the Annotate section, or we can hover over any asset and click the three dots in the bottom right-hand corner, and then click Annotate Asset. If you haven't already added them, you'll be prompted to enter at least one tag to begin annotating. For now, we'll just annotate lungs. We can then click the X and wait for our asset to load. Once loaded, we can see that our volume, or ground truth layer, is displayed in Datature's MPR Annotator, a new addition to our annotation platform. Here, you can view your volumes in a 3D view from multiple perspectives, or as orthogonal projections across the coronal, axial, and sagittal planes. As you can see, we can navigate through slices of our volumes using sliders and shortcuts, as well as customize the viewports for orthogonal projections. To begin, we'll double-click the axial view to select it as our active view and navigate to a slice featuring the lungs, locking the slice in place to annotate. Our MPR Annotator features a number of annotation tools, such as the Rectangle tool, Paintbrush tool, Voxel Brush tool, Polygon tool, FreeDraw tool, and AI-assisted lasso and magic fill tools. For our first annotation, we'll use the magic fill tool. We can click on the tool to load it. Once loaded, we can click and drag to automatically fill the desired area. Release your left mouse button, and you'll be prompted to clean up any holes within the annotation area. Click Clean Up Holes, and then commit your annotation. We see that our annotation still has a couple of holes, despite our cleanup. To modify an annotation, we can click on the annotation and then select the Paintbrush tool to fill in these annotations. Click on the Paintbrush tool and wait for it to load. We can then increase the size and click and draw to fill the holes in our previous annotation. Press space to commit, and now we've mended the holes in our annotation. Let's annotate another slice. We can do so by clicking the plus next to the slider. This will navigate us up a slice. We can select the Magic Fill tool again, but this time we will go into Settings and increase the Magic Fill Cleanup threshold, which increases the threshold for the size of the holes that are actually cleaned up after annotating. Now, let's activate the Magic Fill tool. Click and drag like before. Release and notice that the larger holes are also included in the cleanup. Clean up the holes and now we have a perfectly annotated slice of the lung. Let's try another tool, the lasso. Click S to activate or click the tool itself. With the lasso tool, you set grounding points, and the lasso will predict the boundaries of the mask using edge awareness from the last grounding point and the current mouse position. After moving the mouse, we can click and set a new grounding point, and then drag our mouse to the next point, predicting the mask's outline as we do. When done, click the initial grounding point to complete the mask. We can then press space and annotate this slice. Now we can move on to another slice. You can see that we actually don't need too many grounding points to annotate well. You can also change the threshold for the boundary prediction in the settings that we saw earlier. The final tool that we use is the voxel brush, a volumetric paintbrush which draws with a voxel sphere rather than a pixel circle like the paintbrush does. Here we can draw similarly to the paintbrush tool, annotating the necessary areas. Once annotated, navigate through the slices to see that despite only annotating a single slice, annotations only appear across neighboring slices, speeding up the annotating time. Then, like before, you can edit these annotations on an individual slice using the paintbrush tool. Additionally, if you have existing annotations from another workflow, we provide functionality to load those annotations into the platform. To do so, we need to go to the Dataset tab underneath the Annotate section. From here, go to the Upload/Export Annotations tab. Here, we'll see Upload Annotations, and to the right, there's a button we can click to begin uploading. First, we are prompted to select an upload format. Currently, we support one-hot segmentation using Nifty, class index segmentation using Nifty, and DICOM RT structure set. For our annotations today, we have them stored as class index segmentation using Nifty. Then below, we provide a preview for the expected format. First, what the label file itself should look like. Then, we provide an example of the label.json file, which assigns class IDs in the label files to particular classes. We can then click Next and upload our files in one of two ways, directly on the platform or by using the Python SDK. We will use the platform. Click on the Upload Annotations and select all of your label files. Once selected, click Submit. Your annotations will be uploaded. Then the annotations will be processed in the background, updating you through the Notifications tab when done. Once done, we'll be prompted with a notification in the top right corner telling us our annotation import has succeeded. To check out the annotations, we can head over to the View Assets tab. From here, we can see that each image has been tagged with classes featured in their annotations. To view them, we can go to the annotator or click on a particular asset. Give the annotator a little time to load the assets and annotations. You can now see that the annotations are shown in the annotator. We can explore the annotations in either the 3D view, changing perspective if desired, or we can navigate through the slices across any of the orthogonal views. We can view another asset by clicking on it in the asset gallery at the bottom. Once loaded, we can see the annotations present in this asset. Like before, we can navigate through the slices and observe them through any of the orthogonal views. Now that our assets have been annotated, the asset and annotation statistics on the dashboard will be updated with the classes present in our dataset, giving us information about the counts and frequencies of each class. Moreover, we can now begin our model training. To get started, quick workflow under the model section. From here, there are a couple ways that we can define a workflow. We can either start a quick start training, which will observe our dataset and automatically select the vision task, model size, and optimization best determined for our task. We can also create a custom workflow by navigating back and click the Create Workflow button. From here, we'll enter a workflow title, such as Multi-Organ Segmentation, WF, or Workflow for short. We will then select the medical 3D segmentation vision task, then click Next. We will now choose between a small model and a large model. Here, we might not select a small model because we might be looking to do batch processing of our scans on a workstation, and thus we care most about accuracy. As such, we'll select a large model. Afterwards, we're prompted to select an optimization. For the same reason, we would opt to choose highest accuracy optimization over balanced performance optimization. As such, click highest accuracy, and then click next. We're given a summary of our choices, and we can accept by clicking build model workflow. Now, we're presented with a workflow here, which features 3 modules. The dataset module, which defines what data we will feed into our model through train test splits, seeds, and advanced options. In advanced options, we can customize a few things. We can opt to choose asset groups to train on. However, we only have a main for now, so we'll leave it be. We can also select particular annotation tags to train on. For this training, we'll omit detecting the brain, as it only has 9 instances, so our model may need a bit more annotations before being confident in predicting the brain class. Moreover, we can select particular assets to evaluate during advanced evaluation, more on that later, or certain asset statuses. We also have the augmentations module, which provides us with augmentations to increase the robustness of our dataset, introducing our model to variants that may be encountered in the real world. For example, we may not encounter flip perspectives, so we can remove those. However, different scans, such as MRI or CT, across different modalities and machines, may introduce different intensities, contrast, and intensity windows. As such, we will add augmentations to introduce this variance in the training process. Furthermore, we can enable advanced mode to modify the presence and severity of each of these selected augmentations. Next, we have the model module, which defines a model that we will train on. Currently, we've loaded a Swin UNETR model pre-trained on the BRATS dataset. However, we may want to switch that out. To do so, right-click and hover over Models, which shows the models that we host on Nexus. You can see that we have SegResNet, Swin UNETR, NNUNet3D, and SegMemba. We will use NNUNet3D and select the model not pre-trained on BRATS. We can then delete the previous model module and connect up the new one. From here, we can click on the module and modify its hyperparameters, like batch size, training steps, and the solver. For here, we'll slightly increase the batch size, but leave the number of training steps the same, as well as the solver. Now, to run our training, we can click Run Training. This will prompt us to select a checkpoint strategy for which we have advanced options and multiple strategies to choose from, such as always saves last checkpoint, lowest validation loss, and highest accuracy. Today, we will select lowest validation loss using the total loss metric. Then, we will keep advanced evaluation enabled. After clicking Next, we can configure our hardware acceleration. Datature hosts a number of dedicated cloud GPUs with various GPUs available at any given time. For this training, we'll select 2 NVIDIA L4 GPUs. We also host custom runners, so you're able to use your own instances or cloud-based GPUs. Moving on, we'll click Next and are given a summary of our choices, going over the model architecture, the batch size, the training steps, the total evaluations, and checkpoints generated. We're also given information on our usage, which changes depending on the GPU selected, and other options. If everything looks okay, we can click Start Training and wait for our training to be initialized, ultimately bringing us to our current runs information screen. Fast forwarding to our completed model training, we can view our training statistics. Here, our total loss is a bit noisy, possibly due to an outlier in the training data, but we can smooth it out to clearly visualize the model training. We can see that our evaluation loss is still monotonically decreasing, indicating that we could benefit from more training steps. We also have metrics covering IOU loss, cross-entropy loss, dice loss, and focal loss. Moreover, we have evaluation metrics such as average precision, average recall, IOU score, pixel accuracy, and F1 score. We can then check out the Advanced Evaluation tab to understand how our model learned over time, as well as check out the performance of our final evaluation checkpoint, the model we saved. Here, we see that the model learned fairly well across all classes, but struggled a bit on very fine organs such as the ribs. However, classes like the lungs, liver, kidneys, and bladder seem to do fairly well. We can also select certain classes to view for a clearer picture. We see that some were detected in outlier areas of our assets. We can also head on over to the Confusion Matrix tab to understand how our model learned across individual classes. Overall, it seemed the model performed well on most classes, especially when not considering objects that were truly in the background class. However, the model seemed to not fare too well on the bladder class, with many background pixels being classified as the bladder class. And finally, we also have raw training logs to view at your convenience or to create your own visualizations. Now that we have a trained model, we can think about deploying our model. trained models will be stored as model artifacts in the Artifacts tab under the Model section. From here, we see our trained model. We can click the three dots in the bottom right corner, which gives us some options for viewing the run, exporting the model, and creating a deployment. Exporting a model will allow us to download the model locally and host the model where we want, such as a cloud platform or on Edge. Currently, we only have Onyx models available for NN-UNET 3D, but more formats with advanced exports are available on a wide range of our other models. We can then click generating our model artifact and allowing us to download it later. We can also host the model on Datature's Nexus platform, which allows our model to be accessed via an API endpoint, integrating seamlessly into your existing workflows. First, however, we need to generate our API key. Click on Generate Your API Key, which takes you to the integrations page. Navigate to the API keys and generate your secret key. Be sure to store your secret key in a safe place for later. Now, return back to your artifact and create a deployment. Name the deployment, something such as multi-organ-seg, and give it a version name. Then select the region and artifact you want to deploy, and then click Next. Now we'll select our compute, either CPU-based or GPU-based, each with a number of options to select from. We can choose one and then click Next. Now we have the ability to select whether or not we want to do active learning. Active learning automatically handles sending low-confidence samples within some adjustable threshold to be sent back to the Nexus platform in a separate group and annotated so that a subsequent model can be trained on low-confidence data, ensuring your model is continuously improving over time. Once selected, from here we can click Create Deployment, and our deployment will be hosted and accessible via the Deploy tab underneath the Integrate section. Congratulations! From this project, you've been able to create a multi-organ 3D segmentation model from scratch using Datature's Nexus platform. For more tutorials and information, please check out our documentation and YouTube channel. And if you have any follow-up questions, leave them in the comments or check out our community Slack channel where the community, as well as our engineers, can see and respond to your questions. Thank you.